Just a short blurb here to give context to why we're doing F parallel delta S and all that stuff. Remember that by Newton's second law, A is net force divided by mass. Analysis of uniformly accelerated motion, which is what you get if you have a constant net force and a constant mass, is Vf squared equals V naught squared plus 2A delta S. It's one of the things that comes out of our analysis of uniformly accelerated motion. If we put these two together, we get F net delta S equals 1/2 mVf squared minus 1/2 mV naught squared. Very straightforward. Just a little algebra. We call F net delta S the work done by the net force. We note that 1/2 mVf squared minus 1/2 mV naught squared is the change between our initial and final instant in the quantity 1/2 mV squared. So this is the change in 1/2 mV squared. And 1/2 mV squared we define to be kinetic energy, so this is equal to the change in kinetic energy. This allows us to bypass the details of the analysis of uniformly accelerated motion with a conceptually more sophisticated and often more powerful idea, the idea of work and energy. Okay, work and kinetic energy in this case, and pretty soon we'll see what potential energy is, and then we have at least the beginning of an understanding of the energy concept, which is crucially important to our ability to think through physical situations. Okay, so that's why this is important, and that's why I start the whole thing with projections, or use the projections to start getting a handle on how you get the work when the force is not in the same direction as your displacement. This assumes your force is in the same direction as your displacement. We modify it to F parallel times delta S, and note that that's the same as F times delta S parallel. We'll say a lot more about this.